Hello, this will be lecture 6. We're going to start talking about how we get point defects in the form of impurity atoms into a solid. This image here at the first slide on the left is what's called a diffusion couple at time equals 0. So we have copper on the left and we have nickel on the right, and they're represented by two different colors. After some period of time, we arrive at what's called steady state, and steady state is defined as when this line here, this change in concentration of copper with distance, and this change of concentration of nickel with distance, when they become straight lines. So right in here where this is a straight line and here where this is a straight line, that's steady state. Closer to the surface, where this is changing with depth at a different rate, that's non-steady state, and we'll talk about that at the end of today. Okay, so this is steady state situation, and we can only use these equations in that circumstance. So the equation that will develop here is going to have a few terms that we need to define. Give me 1 second here to get color. Okay, so we're going to have whatever is diffusing in is in high concentration on the left, and we're letting it diffuse across a thin plate that has a surface area equal to A to the low concentration side. And by definition, this concentration gradient, this change in concentration, is always got a negative slope, just like here on the image on the right. So if we looked at two different points in this plate, this would be, X sub A, and this would be X sub B, some different depths. And if we looked at the concentration of whatever it is that's diffusing at those 2 points, the concentration closer to the high concentration side will be high, and the concentration further will be low, and so the concentration gradient will decrease with depth, just like this image on the right. So we have 2 points at which we're taking the measurement. Closer to the surface is A, and further into the center is B, and then we're measuring concentration at both of those. If we get that information, then we can use the steady state equation. And the steady state equation says that J, which is the diffusion flux, or the flow of atoms across an area per unit time, J is equal to negative diffusivity, D, and that times the concentration gradient, dC, dx. So it's a pretty simple, the problems, example problems that you might see, the problems on a quiz, are pretty simple. There's really only, there'll be 2 concentrations and 2 depths different. There's diffusivity and there's diffusion flux. And you'd have 2 of those terms and you'd be solving for the third. So an example of that is this last slide. It says we're diffusing carbon across a thin layer of titanium, and we're measuring the concentration at 2 different places. So if I say here's the surface and here's the other side, I'm going to measure at 1 millimeter below the surface and at 3 millimeters, so that this distance is 2 millimeters. That's the change in X. And the change in concentration is given as 0.68 kilograms per cubic meter closer to the surface. And of course, it's got to be less as we go in toward the center because concentration moves downward. So to C to X is going to be 0.25 minus 0.68. That's kilograms per meter cubed. And in the denominator, we have the change in depth. And that is 2 millimeters. I'm going to say 2 times 10 to the negative 3 meters so that I have meters to the fourth in the denominator. So if I solve that, I get negative 215 kilograms per meter to the fourth. I'm given the flow rate, or J, and I'm asked to find the diffusion coefficient, D. So I'm told that 1.27 times 10 to the negative 9 kilogram across a surface area, meter squared, per unit time, seconds, is equal to negative D times negative 215 kilograms per meter to the fourth. Those negatives will cancel, and I can solve for diffusivity or the diffusion coefficient. D and is going to have units of kilograms per meter squared second divided by kilograms per meter to the fourth. And so it has units of meters squared per second. So diffusion coefficient or diffusivity per meter squared second is going to be equal to 1.27 times 10 to the negative 9 kilograms per meter squared second divided by 215 kilograms per meter to the fourth, which is equal to 5.9 times 10 to the negative 12 meters squared per second. Okay? So that's very basic kind of a problem, very linear, 2 knowns and 1 unknown. All right, that ends this first part of lecture 6.